Hello everyone, I'm Sunggun Kim, a PhD student of Texas A&M University. In this video, I'm going to talk about execution timing of y86-64 sequential processor in Logisim. Okay, I think not many students can easily catch the importance of this timing diagram at the beginning of our term project. But it is okay. Whenever you feel it's important, then you can revisit this tutorial and then fix your own timing diagram. Okay, again, why it is important? Because a certain input to certain module or a certain stage is not always available. So for example, let's think about how many cycles to make input data to the write back stage. So let me annotate on the data path. Okay. So what are the input data to the write back stage? So write back stage is associated with writing data to the register file. So when we look at the register file over here, you see two incoming wire, one from the memory over here, and then the other from the ALU, like here. Okay, so then it is very far from the beginning of the execution stage, fetch stage. So then let's assume it takes at least a couple of cycles, let's say 2-3 cycles, to make these two input data to the register file. Okay, and then if we don't care about this timing, and then we always take this input data and then write to the corresponding register, then it may corrupt data to the register file and then mess up some execution, right? Because we don't know, or we don't know what data will be on this wire, like on for val M or val E, if we didn't actually execute ALU and then get the val E, or we didn't start data memory stage and then get the val M. Then we have an unknown value on this wire, then it is possible to corrupt a certain memory, the contents in this register file. So this is the important to know that we should start writing this input data to the given register when these two inputs are available, right? So that's why we should be careful, or we should know the timing to start executing a certain stages. So we should know when to start fetch stage, when to start decode stage, and so forth. Okay, again, so we need timings of inputs to each stage. Okay, so like when each stage has available inputs. But the timing diagram depends on your design. So based on your configuration of instruction memory, or your actual circuit design, or like gate design for register file design or ALU design, so the cycles to finish a certain stage will be different. So that's why the timing of start timing of each stage will depend on your design. So I recommend you to try drawing this entire timing diagram in the early stage, like maybe fetch stage. But it is okay if you can't come up with this timing diagram. Just make a first stage and then wait until you face the issue with this timing. Then it is the time for you to start drawing this timing diagram. Okay, let's take an example with a simple assumption. So let's assume that every stage can finish its computation in a single cycle. So then based on this assumption, I made a timing diagram of y86 with some information like some wires or registers in this data path. Okay, so let's take a look at this figure in very detail. So it starts with clock signal here, and then it has stage information. So from what cycle to what cycle we are in some stages. Okay, and then we have instruction. So where it indicates from what cycle to what cycle one instruction is available. And then we have ICode, iPhone, RA, RB, RP, VelP, VelC, which is from instruction like fetch stage, and then VelB, VelA, VelB for decoding stage, and then VelE for execution stage, and then VelM for memory stage, and then new PC for PC update stage. So let me clear this ink and then annotate again. Okay. So then for the first edge at cycle 0, we start execution instruction fetch, and then we'll get all the information from the instruction memory and PC increment in a single cycle 0. So then these values will be available in cycle 0, and the next cycle we can use this value in the next cycle, in the next stage. But in the next stage, before we go to the next stage, so as you can see in here, so all the values from the fetch stage are available in the cycle 0, and then they will be used in the next stage. But the next stage, which is decoding stage, is just reading values from the register file. So it doesn't have to be synchronized with clock signal. So as long as the values are available, then it can produce val A and val B. So again, since RA and RB are available in cycle 0, so we can read val A and val B here on the right hand side in the same cycle. So that's why we can execute instruction fetch and decode in a same cycle, like cycle 0. So then at the cycle 0, so val A and val B also available. So in the next cycle, cycle 1, we can start execution stage. Okay, or we can see this way, we can check this way. So we can check all the cycles when all these 3 inputs to ALU are available. So what are the inputs to ALU? So val A here, and val B second, and then val C. So val C, val A, val B are all available in cycle 1, so we can start execution stage. Okay, so then in the execution stage at cycle 1, it will produce value E here, and then this will be available in the next cycle, which is cycle 2, because we assume that every stage can finish its computation in a single cycle. So then in the next cycle, like cycle 2, we can start memory stage. And let's double check whether all the inputs to memory stage are available. So what are the inputs to memory data memory? So here, and then we trace back. Okay, one input is val E, and another input is val A, and then another input is val B and val P. Yeah, I don't see all the things, but the latest the input to the data memory, the ready, is val E, and val E is ready at cycle 2, so we can start memory stage here. Okay, and then it outputs the memory value as an memory value over here, and then in the next cycle we can use write back stage and PC. Okay, let's check inputs to write back stage. So write back stage is actually done by register files. So input to register file is here, the two inputs, one from the val E, which is output of ALU, and then the other input is output of data memory, val M. So val M and val E are available after or at cycle 3 here. So that's why we can start write back stage at cycle 3. And then what about PC update stage? So let's check all the inputs to new PC. So there are 3 input data. So one is val C, and next one is val M, and the last one is what? Okay, is val P. Okay, these 3 values are candidate of next PC. So, and all these 3 inputs to PC update state are ready or available at cycle 3 as well. Okay, so that's why we can start both write back and PC update at cycle 3. And then at cycle 3 it will output next PC, new PC, to fetch next instruction. Okay, so then in this assumption and this diagram, the one instruction execution takes 1, 2, 3, 4, 5 cycles, and then next instruction execution will start at cycle 4. So here. So then based on this information, this timing, so you can actually start operating or start executing each stage. Okay, or otherwise like some register value in each stage will be messed up, and then your output will be wrong. Okay, here I have a useful website for drawing a timing diagram. So as you saw in the previous diagram, I didn't write a timing diagram by myself. I just used this online website to draw timing diagram. You can try using this diagram, but you can find another tool if you are already familiar with. Okay, so this is it, and in this video I talked about timing diagram of y86 x64 implementation. And just keep in mind timing is important for each stage, and you should have your own timing diagram. So but you can you will update a couple of times this timing diagram, because it's not that simple to fix or have a correct timing with one shot. Okay. In the next video, we will finally talk about first stage of our processor, which is fetch stage, using Logisim. Thank you.